Okay, so welcome to part 3 of the course, which is about the semantics of programming languages. So this is a part where we're going to see how to apply proof assistance, well, in our case, Lean, to a realistic and in fact a real application from computer science. And at the same time, I'm not going to assume that you know what semantics is to start with. So you're going to learn both semantics itself and how to formalize it or how to verify it in a proof assistant. So it's a double challenge, you can think of it as. And typically, I think in previous years, this was the favorite part of the students, for the students, but for the computer science students, the math students typically prefer the last 3 or 4 lectures on mathematics. Although these lectures on maths are quite basic, so they're not they're accessible also to computer scientists, including myself. So that shouldn't be a problem. Okay, so we'll start today with one specific type of semantics, which is called operational. So there are 3 main families, if you like, of semantics. We have operational, you have axiomatic, which is also called Hoare logic, after Tony Hoare, and there's a denotational semantics. So it's 3 different types, and it's quite convenient because we have 3 lectures on it, so it really fits each type in one lecture. But at first, I want to start with some general introduction to formal semantics, or why would we want to have a semantics of a programming language. Well, the main idea is, I don't know if you've ever looked at the specification, the official specification, the standard. Oh, why do I wear headphones? So I don't know if you've ever looked, and my hair is all weird. Oh, that's better. So I don't know if you've ever looked at, the C or C++ standard, right? It's a lot of blah blah, right? If you think this course is a lot of blah blah, you haven't seen anything. This is 500-page long, 600 or even more, and they try to specify what happens when this or that happens and so on. So this is an informal semantics, right? This is a semantics in English, a prose semantics, or pen and paper semantics, if you like. And the advantage of a formal semantics is that it's precise. You don't have ambiguities that you inevitably have with the English language. You can really specify what happens under which conditions. In fact, some researchers have formalized the semantics of C and other programming languages, as well as they could, because they started from something that is imprecise, and then they had to make some reasonable assumptions about what is meant in the text, and then stated in a proof assistant. And the advantage, once you have a formal semantics, is that you can use it in verified compilers, in verified interpreters, in verified verifiers, also static analyzers, type checkers, and so on. And without a formal semantics, then these tools tend to be wrong. Especially compiler optimizations tend to be very wrong. So I mean, if you want your program to be compiled correctly, the safest thing to do is to disable all compiler optimizations. And in fact, this is what companies like Airbus are required to do by the certification authorities. So when the software that runs an airplane is not optimized, because that would be too risky. But with a formal semantics and verified compiler and so on, then you can actually turn on the optimizations. And this is something that it's a process has been going on in the past few years, but this is a potential benefit for Airbus, that they can run faster, so more CPU intensive programs on their airplanes, which they really want to, without having to change the hardware. So there are various benefits to having formal semantics, which have to do with correctness, but in the last case also with efficiency of your programs that are compiled with a verified compiler. And one of the nice things about formal semantics is that it's relatively easy to do in a proof assistant. You don't need any fancy math theories. I mean, you don't need perfectoid spaces, for example, right? So you can get started with almost no libraries, which is exactly what we do here in the course. So it's one of the reasons why we chose this as or application to computer science, because there are other applications as well of proof assistance than just formal semantics. It's also the most popular one, probably for that reason. So if you go to a conference like POPL, the Principles of Programming Languages, you're going to see, maybe 10 to 20% of papers presented there are based on a proof assistant. And here's an example. So some quotes, a quote from Conrad Watt, a researcher from Cambridge, and he formalized a language called WebAssembly. So it's a new language, a bit like JavaScript, but better, I hope. And he developed his formalization using Isabelle Proof Assistant at the same time as the WebAssembly standard was developed. So he was able to improve the English prose and clarify some things thanks to his efforts. So it's always better to fix the bugs early than late. But other people have found issues with the Java memory model, but it was 10 years later, right? Or the Java language specification, or any other number of languages and tools and so on. Because if it's done on paper, you can assume it's broken. Something somewhere is broken. Okay.